Hello, and welcome to Space Historians. I'm glad you've joined me, ready to slow down, breathe deeply, and let your thoughts drift weightlessly beyond our world. This is your moment to leave the noise of the day behind and step quietly into the vast, starlit corridors of cosmic discovery. Each episode here isn't just about numbers or equations. It's about the profound question of whether Earth stands alone or walks among countless cousins scattered across the galaxy. If you enjoy these quiet journeys, a like and a subscribe help keep this channel orbiting. But for now, you don't need to do anything but listen. Imagine standing beneath a clear night sky, far from city lights, where the Milky Way stretches overhead like a river of ancient light. You see thousands of stars with your eyes alone, each one a sun burning across unimaginable distances. Now, imagine that nearly every single one of those points of light, every star you see and the billions more you cannot, hosts at least one planet circling in silent orbit. Imagine further that among those countless worlds, tens of billions may be similar in size and distance to Earth, positioned where liquid water could pool on their surfaces, where atmospheres might gather, where conditions could allow life to begin. This is not speculation or wishful thinking. This is what the data now suggests. Our galaxy, the Milky Way, may contain more Earth-like planets than there are people on our own world. The number is so vast it almost slips beyond comprehension, yet it emerges from careful observation, patient calculation, and the relentless work of telescopes that have spent years watching the skies. For most of human history, we could only wonder if other worlds existed. Philosophers debated it, poets imagined it, but no one could prove it. The stars were distant fires, unreachable and unknowable. Planets beyond our solar system were ideas without evidence, possibilities without confirmation. Then, in the last few decades, everything changed. Instruments grew sensitive enough to detect the faintest signals, the tiniest wobbles in starlight, the briefest shadows crossing distant suns. One by one, planets were found orbiting other stars. First a handful, then dozens, then hundreds, then thousands. With each discovery, the picture grew clearer. Planets are not rare. They are everywhere. And if planets are common, then the conditions that shaped Earth, the balance of rock, water, and air, may also be common. The implications are staggering. If billions of Earth-like planets exist, then the question shifts from whether we are alone to how many neighbours we might have. It transforms our sense of place in the universe, suggesting that Earth is not a singular miracle, but one example among countless others. The galaxy, once thought vast and empty, now appears crowded with possibility. Every star you see may be more than a point of light. It may be the centre of a system, a family of worlds, some barren, some strange, and some perhaps carrying oceans, continents, and skies not unlike our own. To grasp this is to stand at the edge of wonder, to realize that the cosmos is far richer, far more generous with worlds than anyone imagined. This journey begins with that single, impossible idea. The galaxy is filled with Earth-like planets, and the number may reach into the tens of billions. How do we know this? What evidence supports such an extraordinary claim? The answers lie in shadows on starlight, in statistical models, in the patient work of scientists who spent years asking one quiet question: how many worlds like ours could be out there, waiting to be found? The story unfolds, not through a single discovery, but through thousands, each one adding weight to the conclusion. It begins with understanding the sheer scale of the galaxy itself, the number of stars that fill its spiral arms, and the realization that nearly all of them have planets. From there, the mathematics become both humbling and thrilling. When astronomers first began counting stars in the Milky Way, they arrived at estimates ranging from 100 billion to 400 billion, depending on how they accounted for faint stars hidden in dust or lost in the glare of brighter neighbours. Even at the lower estimate, 100 billion is a number almost beyond human comprehension. If you tried to count to 100 billion at a rate of one number per second, it would take you more than 3,000 years. And that is just the stars. Each of those stars, as we now know, is likely surrounded by planets. Some have one, some have many, but the average appears to be at least one planet per star. That means the galaxy may contain hundreds of billions of planets, perhaps even 1 trillion or more. Among those planets, a significant fraction are rocky, similar in composition to Earth, Mars, or Venus. Others are gas giants, icy worlds, or strange hybrids we are only beginning to understand. But the question tonight focuses on a specific subset, the rocky planets that orbit within the habitable zone of their stars, the region where temperatures allow liquid water to exist. Water is the foundation of life as we know it, the medium in which chemistry unfolds, the substance that shapes climates and nourishes ecosystems. A planet without water may be geologically interesting, but a planet with liquid water is potentially alive. The habitable zone is therefore the sweet spot, the range of distances from a star where conditions are neither too hot nor too cold. Earth sits comfortably within the Sun's habitable zone, and its oceans have persisted for billions of years. Venus, slightly closer to the Sun, fell victim to runaway greenhouse heating. Mars, slightly farther out, lost its atmosphere and became a frozen desert. The difference is subtle but profound. A few million miles in either direction can shift the outcome dramatically. Yet across the galaxy, billions of stars have their own habitable zones, and within those zones, planets have been found. The discovery of these worlds and the statistical analysis of their abundance is what leads to the astonishing conclusion. Earth-like planets are not rare exceptions. They are common outcomes, scattered throughout the galaxy in numbers that challenge the imagination. The story of discovering Earth-like planets does not begin with telescopes or data, but with a much older human impulse, the urge to look up and wonder. For thousands of years, people across cultures gazed at the night sky and asked whether the stars were more than distant lights. Were they other suns? Did they have worlds of their own? Were there places beyond Earth where life might exist? These questions were not scientific in the modern sense, but they were profound. They touched on humanity's deepest uncertainties about existence, purpose, and solitude. Ancient Greek philosophers debated the possibility of other worlds. Some, like Epicurus, argued that the universe must be infinite and filled with countless Earths. Others, like Aristotle, believed Earth was unique, the only place where the elements combined to create life. For centuries, the question remained unanswerable, trapped in the realm of philosophy and imagination. The invention of the telescope in the early 1600s changed everything. For the first time, humans could see details beyond the naked eye. The mountains and craters of the moons of Jupiter, the rings of Saturn, the phases of Venus. Each discovery expanded the sense of what was possible. If Jupiter had moons, then the universe was more complex than anyone had imagined. If Venus showed phases like the moon, then it orbited the Sun, not Earth. The old models of the cosmos crumbled, replaced by a new understanding. Earth was not the center. It was one planet among several, orbiting an ordinary star. This shift in perspective was profound, but it still left one question unanswered. Did other stars have planets? For centuries, that question remained out of reach. Stars were so distant that even the most powerful telescopes could not reveal details. Planets, if they existed, would be far too faint to see directly. Their light would be overwhelmed by the glare of their parent stars, like trying to spot a firefly next to a searchlight from hundreds of miles away. The challenge seemed insurmountable. Some scientists believed planets must exist around other stars, reasoning that the processes that formed our solar system should be common. Others were skeptical, arguing that without evidence, such beliefs were speculation, not science. The debate simmered for decades, waiting for technology to catch up with imagination. The breakthrough came in the late 20th century, when astronomers developed new techniques to detect planets indirectly. Instead of trying to see the planets themselves, they looked for the effects planets have on their stars. A planet orbiting a star exerts a gravitational pull, causing the star to wobble slightly. This wobble is tiny, but it can be detected by measuring shifts in the star's light. As the star moves toward us, its light shifts slightly toward the blue end of the spectrum. As it moves away, the light shifts toward the red. By tracking these shifts with extreme precision, astronomers could infer the presence of a planet, even if they could not see it. This method, known as the radial velocity technique, became the first reliable way to find planets beyond our solar system. In 1995, two Swiss astronomers, Michel Mayer and Didier Queloz, announced the first confirmed detection of a planet orbiting a Sun-like star. The planet, named 51 Pegasi b, was nothing like Earth. It was a gas giant, similar in size to Jupiter, but it orbited its star in just over 4 days. This was shocking. In our solar system, gas giants orbit far from the Sun, taking years or even decades to complete one orbit. Yet here was a massive planet circling its star at a blistering pace, so close that its surface temperature must be scorching. The discovery defied expectations, but it was undeniable. Other stars had planets. The question had been answered. The announcement sent ripples through the scientific community and beyond. If one star had a planet, how many others did? If planets could be so different from those in our solar system, what other surprises awaited? The discovery of 51 Pegasi b was the beginning of a flood. Within a few years, dozens of exoplanets were found, most of them gas giants orbiting close to their stars. These so-called hot Jupiters were easier to detect because their large size and tight orbits produced strong signals. But they raised new questions. Were rocky planets like Earth rare, or were they simply harder to find? The search intensified, driven by the hope that among the growing catalogue of strange worlds, some might resemble home. The setting for this search was not a single observatory or a single country, but a global effort spanning decades. Telescopes on mountaintops, observatories in deserts, and eventually space-based instruments all contributed. Each new detection added to the data, each new method refined the search. The question of how many Earth-like planets exist in the galaxy could only be answered through patience, persistence, and the collaboration of thousands of scientists. The setting was therefore both physical, the observatories and instruments scattered across the world, and temporal, the slow accumulation of evidence over years and decades. By the early 2000s, the field of exoplanet research had matured. Hundreds of planets had been confirmed, and new methods were emerging. The transit method, which detects planets by the tiny dimming they cause when passing in front of their stars, became increasingly important. Unlike the radial velocity method, which favoured large planets. The transit method could detect smaller worlds, including rocky planets similar in size to Earth. This was the key to answering the question of abundance. If small, rocky planets in habitable zones were common, the numbers could be staggering. If they were rare, Earth might be more isolated than we hoped. The stage was set for a mission that would change everything. A telescope designed to stare at thousands of stars and watch for the faint shadows of planets crossing their light. That mission would be called Kepler, and it would reveal the galaxy in a new light. On March 6, 2009, a Delta II rocket lifted off from Cape Canaveral, carrying a spacecraft that would spend the next 4 years staring at a single patch of sky. The mission was called Kepler, named after the 17th century astronomer Johannes Kepler, who discovered the laws of planetary motion. The spacecraft's goal was ambitious and singular: to determine how common planets are in the Milky Way, and specifically, how many of those planets might be similar to Earth. Kepler would not travel to distant stars or take close-up images of alien worlds. Instead, it would watch, patiently and precisely, measuring the brightness of over 150,000 stars simultaneously, looking for the telltale sign of a planet passing in front of its star. This sign, a brief and subtle dimming of starlight, is called a transit. When a planet crosses between its star and our line of sight, it blocks a tiny fraction of the star's light. For an Earth-sized planet transiting a Sun-like star, the dimming is less than 1%, often just a few parts in 10,000. Detecting such a faint signal requires extraordinary precision and stability, which is why Kepler was placed in space, far from the turbulence of Earth's atmosphere. The concept behind Kepler was simple but powerful. By monitoring thousands of stars continuously for years, the mission could detect multiple transits from the same planet, confirming its existence, measuring its orbital period. From the depth of the dimming, astronomers could calculate the planet's size relative to its star. From the frequency of transits, they could determine its distance from the star and whether it lay within the habitable zone. Over time, this data would build a statistical picture of planetary populations, answering questions that had puzzled humanity for centuries. Are planets common? Are small, rocky planets rare or abundant? How many stars host planets in their habitable zones? These were the mysteries Kepler was designed to solve. The first results arrived within months. Kepler detected hundreds of candidate planets in its initial data release, more than had been confirmed in the entire history of exoplanet research up to that point. The candidates required careful follow-up to rule out false positives, but the sheer number was astonishing. It became clear almost immediately that planets were not rare. They were everywhere. As the mission continued, the catalogue grew. By the end of its primary mission in 2013, Kepler had identified thousands of planet candidates and confirmed hundreds of them. Among these were planets of all kinds: gas giants, ice giants, super-Earths, and rocky worlds similar in size to our own planet. The diversity was stunning, revealing that planetary systems come in countless configurations, some familiar, others utterly alien. But the true spark of mystery came when astronomers began analysing the data for small, rocky planets in habitable zones. Early in the mission, Kepler discovered Kepler 22b, a planet about 2.5 times the size of Earth, orbiting a Sun-like star in the habitable zone. It was the first confirmed planet in the habitable zone of a star similar to our Sun. The discovery made headlines worldwide. Artists created renderings of what the planet might look like, imagining blue skies and oceans under a warm sun. Scientists were more cautious, noting that the planet's larger size might make it more like a mini Neptune than a true Earth twin. but the significance was undeniable. Habitable zone planets were real, and they could be found. More discoveries followed. Kepler 452b, sometimes called Earth's cousin, was found orbiting a star remarkably similar to the Sun, lying squarely in the habitable zone. Kepler 186f, an Earth-sized planet in the habitable zone of a red dwarf star, showed that even smaller, cooler stars could host such worlds. With each announcement, the picture grew clearer. The galaxy was not stingy with habitable zone planets. They existed around different types of stars, at different distances, in different regions of the galaxy. The mystery was no longer whether they existed, but how many there were. Kepler's data allowed scientists to perform statistical analyses that had never been possible before. By examining the rate at which planets of different sizes appeared in the data and correcting for the biases inherent in the transit method, astronomers could estimate the true abundance of planets in the galaxy. The transit method favours planets that orbit edge-on to our line of sight and planets that pass in front of their stars frequently. Small planets far from their stars are harder to detect because their transits are infrequent and faint. By accounting for these limitations, researchers could extrapolate from the sample to the full population of planets in the Milky Way. The results were extraordinary. One of the most widely cited studies, published in 2013, estimated that roughly 20% of Sun-like stars host an Earth-sized planet in the habitable zone. If true, this meant that in a galaxy with tens of billions of Sun-like stars, there could be billions of potentially habitable worlds. Other studies, using different methods and definitions, arrived at similar conclusions. Some placed the fraction slightly lower, others slightly higher, but the consensus was clear. Earth-like planets are not rare. They are common outcomes of planet formation, scattered throughout the galaxy in staggering numbers. The spark of mystery ignited by Kepler's discoveries was not just scientific but philosophical. If billions of Earth-like planets exist, what does that mean for life? How many of those worlds might actually be inhabited? How many might host intelligent civilizations? These questions, once the domain of science fiction, had become legitimate scientific inquiries, grounded in data and observation. Kepler had not answered them, but it had shown that the answers were within reach. The mission had transformed the search for life from a speculative dream into a measurable goal. It had revealed that the galaxy is rich with possibilities, that Earth is not alone in being a rocky planet in a habitable zone. The mystery now was not whether such worlds exist, but how to study them, how to detect their atmospheres, how to search for signs of life. Kepler had opened the door, and the journey through it had only just begun. When the first wave of Kepler's discoveries reached the public, the response was a mixture of awe, excitement, and disbelief. For scientists who had spent decades searching for even a single exoplanet, the sudden abundance felt almost surreal. Hundreds, then thousands of planets appeared in the data, each one a new world with its own orbit, size, and story. The field of exoplanet research, once a niche area pursued by a handful of dedicated astronomers, exploded into mainstream attention. Universities launched new research programs, conferences filled with presentations on planetary atmospheres, habitability, and detection methods. Funding agencies recognized the significance and invested in next-generation instruments. The dream of finding another Earth, once distant and abstract, suddenly felt within reach. For the general public, the discoveries sparked imaginations in ways that few scientific findings ever do. News outlets ran headlines about Earth's twin or cousin, accompanied by artists' renderings of alien landscapes. Social media buzzed with conversations about life on other planets, about the possibility of contact, about what it might mean to know we are not alone. People who had never thought deeply about astronomy found themselves gazing at the night sky with new wonder, realizing that the stars they saw were not just distant lights, but potential homes to other worlds. The cultural impact was profound, touching everything from literature and film to philosophy and religion. Among scientists, the response was more measured but no less enthusiastic. Astronomers who had built careers on the assumption that planets might be rare now had to adjust their thinking. The data was clear. Planets were not exceptional. They were the rule. This realization forced a shift in perspective. If nearly every star has planets, then the galaxy is far more complex and populated than previous generations had imagined. The focus of research shifted from simply finding planets to understanding them, to categorizing their types, studying their atmospheres, and determining which ones might truly be habitable. The question was no longer are there other planets, but which of those planets are most like Earth. Yet alongside the excitement, there was also skepticism and caution. Some scientists warned against over-interpreting the data. Just because a planet is Earth-sized and orbits in the habitable zone does not mean it is habitable. Venus, after all, sits within the Sun's habitable zone, yet its surface is hot enough to melt lead. Mars, on the outer edge, is a frozen desert. Size and distance are necessary conditions for habitability, but they are not sufficient. A planet needs the right atmosphere, the right chemistry, the right geological activity, and the right stability over billions of years. Without detailed observations of individual planets, it was impossible to know how many of Kepler's candidates were truly Earth-like in more than just size and orbit. This tension between hope and caution defined the early response to Kepler's findings. On one side were those who embraced the statistical argument, pointing to the sheer numbers. If there are billions of candidates, even if only a small fraction are truly habitable, the total could still be enormous. On the other side were those who emphasized the complexity of habitability, arguing that Earth's conditions might be rarer than the statistics suggest. Both perspectives were grounded in evidence, and both contributed to a richer understanding of the question. The debate was not about whether Earth-like planets exist, but about how common they truly are and what it would take to confirm their habitability. Public figures also weighed in, adding their voices to the conversation. Carl Sagan, though he had passed away before Kepler launched, had long advocated for the search for extraterrestrial life, and his words echoed in the excitement surrounding the mission. Neil deGrasse Tyson, Bill Nye, and other science communicators spoke about the significance of the discoveries, emphasizing that humanity was living through a moment of unprecedented revelation. For the first time in history, we could say with confidence that other worlds exist, and that some of them might resemble our own. The awe in their voices reflected a deeper truth. This was not just a scientific achievement. It was a milestone in human self-understanding. Religious communities responded in diverse ways. Some saw the discoveries as confirmation of divine creativity, evidence that the universe is far richer and more wondrous than previously imagined. Others wrestled with theological questions. If life exists elsewhere, what does that mean for humanity's place in creation? Are we unique, or are we one among many? These questions had been debated for centuries, but Kepler's findings gave them new urgency. For many, the discoveries deepened faith rather than challenging it, revealing a cosmos more vast and mysterious than any doctrine had described. For others, the findings prompted reflection, inviting a broader understanding of existence and purpose. Artists and writers also found inspiration in the data. Science fiction, which had long imagined alien worlds, now had real examples to draw from. Stories set on Kepler planets began to appear, grounded in the actual characteristics of these distant worlds. Visual artists created images of habitable zone planets, some realistic, others speculative, all attempting to capture the wonder of what these places might be like. Musicians composed pieces inspired by the sense of cosmic connection, using soundscapes to evoke the vastness of space and the intimacy of discovering another Earth. The cultural response was as varied as humanity itself, but it shared a common thread, a sense that something fundamental had shifted. In schools and universities, the discoveries became teaching moments. Educators used Kepler's findings to engage students in science, showing them that the questions they asked as children, "Are there other planets? Could there be life out there?" were not only valid but answerable. The sense of possibility energized a new generation of scientists, inspiring students to pursue careers in astronomy, planetary science, and astrobiology. The impact on education was subtle but lasting, planting seeds that would grow into future discoveries. Yet for all the excitement, there was also a quiet undertone of humility. The vastness of the numbers, billions of planets, tens of billions of potential Earths, reminded people of their smallness in the cosmic scale. It was both humbling and comforting. Humbling because it showed that Earth is not the center of anything, that we occupy an ordinary place in an ordinary galaxy. Comforting because it suggested we might not be alone, that the universe is filled with possibility, that somewhere out there, other worlds might carry their own stories. The first response to Kepler's discoveries was therefore layered, mixing awe with disbelief, hope with caution, wonder with humility. It was a response that reflected the complexity of the discovery itself, a moment when humanity looked outward and saw not emptiness, but abundance. The announcement that billions of Earth-like planets might exist in the galaxy created a curious paradox. On one hand, the numbers seemed almost too large to believe. Tens of billions of worlds, scattered across the Milky Way, each potentially harboring conditions similar to our own. On the other hand, we had never directly observed a single one of these planets in detail. We could not see their surfaces, their oceans, their atmospheres. We could only infer their existence from indirect signals, tiny dips in starlight, subtle wobbles in stellar motion, faint spectral signatures. The contradiction was profound. How could we claim to know so much about planets we could not even see? How could statistics derived from shadows and wobbles lead to such sweeping conclusions? This tension between evidence and inference, between measurement and imagination, defined the scientific challenge. The root of the contradiction lies in the nature of astronomical observation. Unlike laboratory experiments, where scientists can manipulate variables and test hypotheses directly, astronomy is a passive science. We cannot travel to distant stars, collect samples, or conduct controlled experiments. We must work with the light that reaches us, interpreting signals that have traveled for years, decades, or even centuries. This limitation requires creativity and rigor in equal measure. Astronomers must develop methods to extract information from the faintest signals, to separate real phenomena from noise, to build models that match observations without over-interpreting them. The process is painstaking and often uncertain, yet it has proven remarkably successful. The transit method, Kepler's primary tool, exemplifies this contradiction. When a planet passes in front of its star, it blocks a tiny fraction of the light. For an Earth-sized planet transiting a Sun-like star, the dimming is less than 1%, often closer to 1/100th of 1%. Detecting such a subtle change requires measuring the brightness of a star with extraordinary precision. accurate to a few parts per million. Even then, the signal can be confused with other phenomena. Stars themselves vary in brightness due to sunspots, flares, or oscillations. Instrumental noise, cosmic rays, and background stars can all mimic the signature of a transit. Distinguishing a real planet from a false positive requires careful analysis, often involving multiple observations and independent confirmation from other telescopes. This difficulty led some skeptics to question the early claims about planetary abundance. How could we trust results based on such faint signals? What if the models were wrong? What if the corrections for observational biases were too optimistic? These were legitimate questions, and they drove astronomers to refine their methods, to cross-check results, to seek independent confirmation. Over time, the evidence became overwhelming. Planets detected by the transit method were confirmed by radial velocity measurements. Statistical models were tested against larger data sets and found to be robust. The skepticism, rather than undermining the findings, strengthened them by forcing scientists to be rigorous and transparent. Yet, the contradiction persisted in a deeper sense. Even as the evidence for billions of Earth-like planets grew, the mystery of what those planets are actually like remained. We could estimate their size, their orbit, their distance from their star, but we could not say with certainty whether they had atmospheres, oceans, continents, or life. The gap between detection and characterization was vast. A planet might be the right size and in the right place, but without detailed observations, it remained a cipher, a statistical entry rather than a real world. This gap became the focus of intense research. How could we move beyond detection to understanding? How could we peer into the atmospheres of distant worlds and search for the chemical signatures of habitability or life? The tension between science and mystery also touched on philosophical questions. Science thrives on evidence, on measurable quantities, on hypotheses that can be tested and falsified. Yet the search for Earth-like planets often felt like an exercise in imagination. We were using mathematics to infer the existence of worlds we might never visit, whose surfaces we might never see, whose nature we could only guess at. Some critics argued that this was speculation dressed up as science, that without direct observation the claims were premature. Supporters countered that this was exactly how science progresses, by building models, testing them against data, and refining them over time. The planets might be invisible, but their effects were measurable, and those effects told a consistent story. Another layer of contradiction emerged in the definitions themselves. What does it mean for a planet to be Earth-like? Is it enough to be rocky and in the habitable zone? Or must it also have the right atmosphere, the right chemistry, the right magnetic field, the right moon? As the criteria became more specific, the number of truly Earth-like planets might shrink. Conversely, if we broaden the definition to include moons with subsurface oceans or planets with exotic chemistries, the number could grow. The contradiction here was one of language and expectation. The term Earth-like promised familiarity, yet the universe might produce habitability in forms we do not yet recognize. This contradiction also extended to the cultural response. The public celebrated the idea of billions of Earth-like planets, imagining worlds with blue skies and green landscapes. Yet the reality, as scientists understood it, was far more uncertain. Most of these planets would never be studied in detail. We might never know if they have water, air, or life. The gap between the statistical reality and the imagined reality created a tension that was difficult to resolve. Science could provide probabilities, but it could not provide certainty. The mystery remained intact even as the evidence accumulated. Despite these contradictions, the scientific consensus grew stronger. The data from Kepler, combined with observations from other telescopes and missions, painted a consistent picture. Planets are common, small rocky planets are abundant, and many of them orbit in habitable zones. The contradictions did not undermine this conclusion. Instead, they highlighted the challenges of astronomical research, the need for patience, rigor, and creativity were intertwined. The more we learned, the more questions emerged. The more planets we found, the more we wanted to know about them. The contradiction was not a flaw but a feature, a reminder that the universe is vast, complex, and endlessly surprising. The search for Earth-like planets was not just about counting worlds. It was about pushing the boundaries of knowledge, about learning to see the invisible, about daring to ask questions that had no easy answers. As the evidence for billions of Earth-like planets accumulated, scientists and thinkers began to divide into camps, each with its own interpretation of what the data meant. The question was no longer whether such planets exist, but what their existence implies. Are Earth-like planets common enough that life should also be common? Or are there hidden factors that make true habitability far rarer than the statistics suggest? The debate that emerged was not acrimonious, but it was passionate. On one side stood those who embraced the principle of mediocrity, the idea that Earth is ordinary and that what happened here is likely to happen elsewhere. On the other side were those who advocated for the rare Earth hypothesis, the notion that our planet is the product of an extraordinary convergence of circumstances, unlikely to be repeated often. Between these two poles lay a spectrum of views, each grounded in evidence, each reflecting different assumptions about the nature of life and the universe. The mediocrity principle has deep roots in the history of science. For centuries, humanity believed it occupied a special place in the cosmos. Earth was thought to be the center of the universe, the sun and stars revolving around it. Copernicus shattered that illusion, showing that Earth orbits the sun. Later discoveries revealed that the sun is just one star among hundreds of billions, and the Milky Way is just one galaxy among countless others. At each step, humanity's sense of centrality diminished. The mediocrity principle extends this pattern, arguing that we should not assume Earth is special. If planets are common, if the ingredients for life, water, carbon, energy, are widespread, then life itself is likely common. This view is optimistic, even egalitarian. It suggests that the universe is fertile, that biology emerges naturally wherever conditions allow, and that Earth is one example among many. Supporters of the mediocrity principle point to the rapid emergence of life on Earth. Microbial life appeared within a few 100 million years after the planet cooled, suggesting that once conditions stabilize, life arises quickly. If this is true here, why not elsewhere? The chemistry that produces amino acids, nucleotides, and other building blocks of life is universal. The same elements exist throughout the galaxy. The same physical laws apply. If life is a natural outcome of chemistry and energy, then billions of habitable planets should lead to billions of inhabited planets. The mediocrity principle does not claim certainty, but it argues that the burden of proof lies with those who claim Earth is rare. Extraordinary rarity requires extraordinary explanation. The rare Earth hypothesis, articulated most famously by Peter Ward and Donald Brownlee in their book of the same name, challenges this optimism. It argues that while simple microbial life may be common, complex life, and especially intelligent life, is exceedingly rare. The reasoning is based on the multitude of factors required for long-term habitability. Earth is not just in the habitable zone. It has plate tectonics, which recycle carbon and regulate climate. It has a large moon, which stabilizes its axial tilt and prevents chaotic climate swings. It has a magnetic field generated by a molten core which shields the atmosphere from solar wind. It has Jupiter, whose gravity deflects many comets and asteroids that might otherwise bombard the inner planets. It orbits a stable, long-lived star that does not flare violently. Each of these factors contributes to Earth's habitability, and each one is not guaranteed. Remove any one, and the outcome might be very different. The rare Earth hypothesis does not deny that billions of planets exist in habitable zones. It acknowledges the statistics, but it argues that most of those planets will lack one or more critical ingredients. Some will be tidally locked, with one side perpetually facing their star. Some will orbit red dwarfs that flare frequently, stripping atmospheres and sterilizing surfaces. Some will lack the geological activity needed to regulate climate over billions of years. Some will be bombarded by impacts too often for complex life to gain a foothold. The hypothesis suggests that while the galaxy may be filled with planets, very few will maintain the delicate balance required for life to not just appear, but to persist and evolve into complex forms. The debate between these two views is not purely academic. It shapes how we search for life and what we expect to find. If the mediocrity principle is correct, then biosignatures should be detectable on many planets. Oxygen, methane, and other signs of life might appear in the atmospheres of numerous worlds. If the rare Earth hypothesis is correct, then biosignatures will be exceedingly difficult to find. We might detect thousands of habitable zone planets and find none with life. The difference is profound, and it influences how we allocate resources, design missions, and interpret ambiguous signals. A third perspective, often overlooked, occupies the middle ground. It acknowledges that Earth may be rare in some respects, but argues that the galaxy is so vast that even rare events can happen many times. If only 1 in a million habitable zone planets develops complex life, that still leaves tens of thousands in the Milky Way alone. This view combines the statistical power of large numbers with the caution of the rare Earth hypothesis. It suggests that life may not be everywhere, but it is not unique either. The galaxy may host scattered pockets of life, separated by vast distances but connected by the shared chemistry of existence. Another theory, sometimes called the Gaian hypothesis, suggests that life itself shapes habitability. On Earth, life has transformed the atmosphere, creating oxygen, regulating carbon dioxide, and influencing climate. Without life, Earth's atmosphere would be very different, perhaps more like that of Venus or Mars. If life modifies its environment to sustain itself, then habitable planets might be those where life has already taken hold. This creates a feedback loop. Life makes a planet more habitable, which allows more life to flourish. The implication is that truly habitable planets may be those that are already inhabited. Detecting biosignatures would then be not just a sign of life, but a sign of a planet that has become more Earth-like through the presence of life. The division of minds reflects the complexity of the question. There is no simple answer, no single theory that accounts for all the variables. The galaxy is too large, the data too incomplete, the factors too numerous. Each perspective contributes something valuable. The mediocrity principle reminds us not to assume uniqueness without evidence. The rare Earth hypothesis reminds us not to underestimate the complexity of habitability. The middle ground reminds us that even rare events, given enough opportunities, become probable. Together, these theories frame the search for Earth-like planets as a question not just of numbers, but of understanding. of asking what it truly takes for a world to sustain life over billions of years. The theoretical debates, while intellectually stimulating, could not be resolved through argument alone. What was needed was data, vast amounts of it, collected systematically and analysed rigorously. The pursuit of Earth-like planets required not just philosophy but engineering, the design and deployment of instruments capable of detecting the faintest signals across immense distances. This pursuit became a coordinated effort involving space agencies, universities, and international collaborations. It required patience, funding, and the willingness to invest years, even decades, in missions whose outcomes were uncertain. The investigation into how many Earth-like planets exist in the galaxy was not a single project but a sustained campaign, a scientific endeavour that spanned generations. Kepler was the flagship of this effort, but it was not alone. Ground-based telescopes contributed as well, using radial velocity measurements to detect planets through the wobble they induce in their stars. High-resolution spectrographs, capable of measuring tiny shifts in starlight, were installed on some of the world's largest telescopes. Observatories in Chile, Hawaii, and the Canary Islands joined the search, each adding to the growing catalogue of exoplanets. The data from these observations complemented Kepler's transit detections, providing independent confirmation and revealing details about planetary masses, densities, and orbits. Together, space-based and ground-based efforts created a comprehensive picture. As the catalogue grew, astronomers developed sophisticated statistical methods to analyze it. Simply counting detected planets was not enough. The data had to be corrected for observational biases. The transit method, for example, only detects planets whose orbits are aligned edge-on to our line of sight. For every planet detected, there could be many more whose orbits are tilted and thus invisible to us. Similarly, larger planets and those orbiting close to their stars are easier to detect than smaller, more distant ones. To estimate the true abundance of Earth-like planets, scientists had to account for these biases, using probability models and simulations. The process was complex, but the results were consistent across multiple studies. Roughly 1 in 5 Sun-like stars appeared to host an Earth-sized planet in the habitable zone, a fraction that implied billions of such worlds in the Milky Way. The investigation also extended beyond detection to characterization. Finding a planet was only the first step. Understanding it required studying its atmosphere, its composition, its climate. This was far more challenging. Atmospheres could be studied during transits. When a planet passes in front of its star, some of the starlight filters through the planet's atmosphere, leaving faint absorption lines that reveal the presence of gases. The technique, called transmission spectroscopy, required extraordinary precision. The signal was minuscule, often just a few parts per million in the overall spectrum. Early attempts focused on large, hot planets with thick atmospheres, where the signals were stronger. But as instruments improved, smaller planets became accessible. The launch of the James Webb Space Telescope in late 2021 marked a new era in this pursuit. Webb was designed with exoplanet atmospheres in mind. Its infrared instruments could detect molecules like water vapor, carbon dioxide, methane, and potentially even oxygen. Unlike Kepler, which found planets by the thousands but could not study them individually, Webb could focus on specific targets, probing their atmospheres in unprecedented detail. Early observations confirmed its capabilities. Within months of operation, Webb had analysed the atmospheres of several exoplanets, detecting water vapor and carbon dioxide. These were not Earth-like planets. Most were gas giants or super-Earths. But the success demonstrated the technique. The next step would be to apply it to smaller, rocky planets in habitable zones. Parallel to these efforts, missions like TESS, the Transiting Exoplanet Survey Satellite, broadened the search. Unlike Kepler, which stared at a fixed patch of sky, TESS scanned nearly the entire sky, focusing on nearby stars. Its goal was to find planets close enough for detailed follow-up with Webb and future telescopes. TESS discovered thousands of candidates, including several Earth-sized planets in habitable zones. One of the most notable was TOI 700d, an Earth-sized planet orbiting a small, cool star about 100 light-years away. TESS provided the discovery, and Webb was poised to study its atmosphere. The collaboration between missions exemplified the coordinated nature of the investigation. The pursuit was not limited to existing planets. Scientists also studied the process of planet formation itself, seeking to understand how rocky planets assemble and what factors determine their final characteristics. Observations of protoplanetary disks, the swirling clouds of gas and dust around young stars, revealed the raw materials and conditions from which planets emerge. These studies showed that the ingredients for rocky planets, silicates, metals, water, are common in star-forming regions. The implication was that Earth-like planets are not flukes, but natural outcomes of a well-understood process. This reinforced the statistical arguments and provided a theoretical foundation for the observed abundance. The investigation also involved the search for biosignatures, the chemical signs of life. While no definitive biosignatures had been detected as of the early 2020s, oxygen, in combination with methane, for example, would be a powerful indicator, since the two gases react quickly and must be constantly replenished. Detecting such a combination in the atmosphere of an Earth-sized planet in the habitable zone would be a landmark discovery, though confirming it as biological rather than geological would require careful analysis. The pursuit of biosignatures represented the ultimate goal of the investigation, the step beyond asking how many Earth-like planets exist to asking how many are inhabited. Throughout this investigation, the role of collaboration was essential. Data was shared openly, published in peer-reviewed journals, and made available to the global scientific community. Conferences brought together experts from different fields: astronomers, planetary scientists, astrobiologists, each contributing insights. The pursuit of Earth-like planets was a collective effort, driven not by individual glory but by shared curiosity. This spirit of collaboration ensured that the results were robust, tested by independent teams, and subject to rigorous scrutiny. It also meant that progress, while sometimes slow, was steady and cumulative, building toward answers that would reshape humanity's understanding of its place in the cosmos. The pursuit of Earth-like planets generated an avalanche of data, far more than any individual or team could analyze alone. Every night, telescopes around the world and in space collected photons, tiny particles of light that had traveled for years, sometimes centuries, to reach us. Each photon carried information, encoded in its wavelength, intensity, and timing. Together, these fragments of light formed patterns, brightness curves, spectra, transit signals that revealed the presence and nature of distant worlds. The data was raw and noisy, filled with artifacts and uncertainties, but buried within it were clues about the galaxy's population of planets. Extracting those clues required patience, skill, and sophisticated algorithms. It required scientists to sift through millions of measurements, separating signal from noise, identifying genuine transits, and ruling out false positives. The process was painstaking, but it was also exhilarating. because each confirmed detection added a new world to humanity's growing map of the cosmos. Kepler's dataset was among the largest ever collected for a single astronomical mission. Over its lifetime, the spacecraft monitored more than 150,000 stars, measuring their brightness every 30 minutes, for years. The resulting dataset contained billions of individual measurements, enough to fill thousands of hard drives. Processing this data required custom software, powerful computers, and teams of analysts working in shifts. The first step was to create light curves, graphs showing how the brightness of each star changed over time. Most stars showed small variations due to intrinsic activity, pulsations, spots, or flares. But a few displayed the characteristic pattern of a transit, a periodic dip in brightness, repeating at regular intervals. Identifying transits was not straightforward. Many signals looked like transits, but were caused by other phenomena. Eclipsing binary stars, where two stars orbit each other and periodically block each other's light, could mimic the signal of a planet. Background stars, blended with the target star in the image, could create false dips. Even instrumental artifacts, glitches in the detector, or variations in the spacecraft's pointing, could produce patterns that resembled transits. Distinguishing real planets from these imposters required multiple lines of evidence. Analysts looked for consistency, transits that repeated with the same depth and duration. They checked for secondary eclipses, slight increases in brightness when the planet passed behind the star, a sign that the signal was real. They used follow-up observations with other telescopes to confirm the planet's existence and rule out alternative explanations. The data also revealed unexpected diversity. Planets came in sizes and types not seen in our solar system. Super-Earths, rocky planets larger than Earth but smaller than Neptune, were common. Mini-Neptunes, gaseous planets with thick atmospheres but not as massive as Jupiter, appeared frequently. Hot Jupiters, gas giants orbiting so close to their stars that they completed an orbit in just a few days, challenged existing theories of planet formation. Each category added complexity to the picture. The galaxy's planetary systems were not uniform. They varied widely in architecture, composition, and history. This diversity was itself a clue, suggesting that planet formation is a flexible process, capable of producing many outcomes depending on the conditions. Among the most important clues were the small, rocky planets in habitable zones. These were harder to detect than larger planets, and they appeared less frequently in the data, but they were there. Planets like Kepler 452b, Kepler 186f, and dozens of others provided direct evidence that Earth-sized worlds in temperate orbits exist. By counting how often such planets appeared and correcting for the biases of the transit method, astronomers could estimate their true abundance. The numbers varied depending on the exact definition of Earth-like, but most studies converged on a similar conclusion. Roughly 10 to 20% of Sun-like stars host an Earth-sized planet in the habitable zone. For red dwarfs, the fraction might be even higher, perhaps 30 to 50%. These fractions, combined with estimates of the total number of stars in the galaxy, led to the headline numbers. If there are 100 billion stars in the Milky Way, and 10% of them host an Earth-sized planet in the habitable zone, that yields 10 billion such planets. If the fraction is 20%, the number doubles to 20 billion. These are staggering totals, but they are grounded in real data. In the thousands of planets detected by Kepler and other missions, in the statistical corrections that account for undetected worlds, in the models that extrapolate from the sample to the full population, the data, for all its noise and uncertainty, pointed in one clear direction: abundance. Yet the data also highlighted gaps in our knowledge. Most of the planets detected by Kepler were hundreds or even thousands of light years away, too distant for detailed follow-up. We knew their sizes and orbits, but little else. Did they have atmospheres? Were their surfaces rocky or icy? Did they have water, clouds, continents? The data could not answer these questions. It provided a census, but not a portrait. To fill in the details, new instruments were needed, telescopes capable of studying individual planets in depth. This was the motivation behind missions like the James Webb Space Telescope and future concepts like the Habitable Exoplanet Observatory. The data from Kepler had shown us where to look. Now we needed to look closer. Another clue hidden in the data was the role of stellar type. Sun-like stars, classified as G-type, make up a significant fraction of the galaxy's population, but they are outnumbered by cooler, smaller stars known as red dwarfs or M-type stars. These stars are far more common, accounting for perhaps 70% of all stars in the Milky Way. If red dwarfs commonly host planets in their habitable zones, the total number of potentially habitable worlds could be much higher than estimates based on Sun-like stars alone. Data from Kepler and other missions suggested that red dwarfs do indeed host such planets, often in tight orbits where the habitable zone lies close to the star. This expanded the scope of the search and raised new questions. Are planets around red dwarfs truly habitable? Or do stellar flares and tidal locking make them inhospitable? The data provided the clues, but interpreting them required further study. The fragments of data also included non-detections, stars that showed no sign of transiting planets. These were just as important as the detections. They told us that not every star has planets, or at least not planets with orbits aligned for transits. By analysing both detections and non-detections, astronomers could refine their models and avoid overestimating planetary abundance. The scientific method thrives on such rigour, on testing hypotheses against all available evidence, not just the most exciting results. The data, in its totality, provided a balanced picture, one that acknowledged uncertainty while pointing toward clear trends. The clues and fragments, assembled over years of observation and analysis, formed a coherent story, a story of a galaxy rich with planets, many of them small, rocky, and orbiting in the zones where life might take hold. Beneath the headline numbers, beneath the statistics and the catalogues of exoplanets, lay a deeper mystery, one that the data hinted at but could not fully resolve. It was the question of what lies hidden on those distant worlds, what secrets they hold beyond their size and orbit. The discovery that billions of Earth-like planets may exist in the galaxy was extraordinary, but it also raised a more profound question. How many of those planets are not just Earth-like in dimension, but Earth-like in character? How many have atmospheres, oceans, continents, weather, life? The data could tell us where these planets are and how common they might be, but it could not yet tell us what they are truly like. This gap between detection and understanding became the deeper mystery, the hidden truth that astronomers were only beginning to uncover. The transit method, for all its power, reveals only the most basic properties of a planet. When a planet passes in front of its star, the depth of the dimming tells us the planet's size relative to the star. The frequency of transits tells us the orbital period, and, from that, the distance from the star. These measurements allow us to place the planet on a diagram, plotting size against temperature, determining whether it lies in the habitable zone. But they say nothing about the planet's surface, its composition, its atmosphere, or its history. A planet that appears Earth-like in this simple sense could be a barren rock, a water world with no land, a planet with a toxic atmosphere, or a world covered in ice. The hidden truth is that Earth-like is a spectrum, not a binary, and most planets in the habitable zone likely differ from Earth in significant ways. To uncover this hidden truth, astronomers turn to atmospheric studies. When a planet transits its star, a tiny fraction of starlight passes through the planet's atmosphere before reaching us. This light carries the fingerprint of gases in the atmosphere, absorption lines at specific wavelengths corresponding to molecules like water vapor, carbon dioxide, methane, oxygen, and others. By analyzing the spectrum of this light, scientists can infer the atmospheric composition. The technique, called transmission spectroscopy, is extraordinarily challenging. The signal is faint, often just a few parts per million, and it requires precise instruments and careful analysis. Early applications focused on large, hot planets with thick atmospheres, where the signals were stronger, but as technology improved, smaller and cooler planets came within reach. The James Webb Space Telescope represented a leap forward in this effort. Its infrared instruments, designed specifically for studying exoplanet atmospheres, could detect molecules that previous telescopes could not. Within its first year of operation, Webb analyzed the atmospheres of several exoplanets, confirming the presence of water vapor, carbon dioxide, and other gases. These were proof-of-concept observations, demonstrations that the technique works. The next step was to apply it to smaller, rocky planets in habitable zones. If Webb or future telescopes could detect oxygen or methane in the atmosphere of such a planet, it would be a landmark discovery. Oxygen, in particular, is unstable and reactive. On Earth, it persists in the atmosphere only because it is constantly replenished by photosynthesis. Detecting oxygen on another planet could be a sign of life, though it would require careful analysis to rule out non-biological sources. The hidden truth also extended to the interiors of these planets. Earth's habitability depends not just on its atmosphere, but on its geology. Plate tectonics recycle carbon, regulate climate, and create diverse landscapes. A magnetic field, generated by a molten iron core, shields the atmosphere from solar wind. Volcanic activity releases gases that replenish the atmosphere. These processes are invisible from afar, but they are essential to long-term habitability. We do not yet know how common such processes are on other planets. A planet the same size as Earth, orbiting in the habitable zone, might lack plate tectonics or a magnetic field. It might be geologically dead, unable to sustain the cycles that keep Earth habitable over billions of years. The hidden truth is that habitability is not just about location, but about activity, about the dynamic processes that maintain balance. Another layer of mystery involves moons. In our solar system, several moons, Europa, Enceladus, Titan, are considered potential habitats, not because they orbit in the traditional habitable zone, but because they have subsurface oceans or unusual chemistries. If such moons are common around gas giants in other systems, the number of habitable environments could be far greater than the number of habitable planets. Yet detecting moons around exoplanets is extremely difficult. They are too small and too faint to produce detectable transits in most cases. The hidden truth is that we may be undercounting habitable environments by focusing only on planets and ignoring moons. The mystery deepens when we consider time. A planet may be habitable today, but was not in the past, or vice versa. Earth itself has gone through periods of extreme cold and extreme heat, snowball Earth events and hothouse climates. Life survived these changes, but it required resilience and adaptation. How many of the billions of Earth-like planets in the galaxy have stable climates over billions of years? How many experience catastrophic shifts that make long-term habitability impossible? The hidden truth is that detecting a planet in the habitable zone is only a snapshot, a single moment in a planet's long history. We do not know whether that moment is representative or exceptional. There is also the question of life itself. If life exists on some of these planets, it may not resemble Earth's biology. It may use different chemistry, different solvents, different energy sources. It may thrive in conditions we consider hostile. The search for biosignatures assumes that life elsewhere will produce detectable gases like oxygen or methane. But this assumption is based on a sample size of 1, Earth. The hidden truth may be that life is far more diverse than we imagine, and that some forms of life leave no signatures we can currently detect. This possibility does not diminish the search, but it adds uncertainty. We may be looking for the wrong signals, missing signs of life because we do not yet know what to look for. Despite these mysteries, progress is being made. Each new observation adds a piece to the puzzle. Each new technique refines our understanding. The hidden truth is gradually coming into focus, not all at once, but through the accumulation of evidence. The deeper mystery is not whether Earth-like planets exist. The data confirms they do, but what those planets are truly like beneath the surface of the statistics. This is the question that drives the next generation of telescopes, missions, and research. It is the question that transforms the search from a census into an exploration, from counting worlds into understanding them. There comes a moment in every great scientific endeavour when the accumulation of evidence reaches a critical mass, when scattered observations coalesce into a coherent picture, when uncertainty gives way to clarity. For the search for Earth-like planets, that moment arrived gradually over the course of the 2010s as the data from Kepler and other missions piled up and the statistical analyses became too consistent to ignore. The paradigm shifted. What had once been a hopeful speculation that Earth-like planets might be common became an accepted scientific fact. The galaxy was not a barren place with a few scattered worlds. It was teeming with planets, billions of them, including tens of billions that resembled Earth in size and orbit. This realization was a turning point, not just for astronomy, but for humanity's understanding of its place in the universe. The shift did not happen because of a single discovery, but because of the weight of many. Each new Earth-sized planet in the habitable zone, each refined statistical model, each independent confirmation added to the evidence. By the mid-2010s, multiple research teams using different methods and different data sets were arriving at the same conclusion. Roughly 10 to 20% of Sun-like stars host an Earth-sized planet in the habitable zone. When applied to the estimated 100 billion or more stars in the Milky Way, the numbers were staggering. Even the most conservative estimates yielded billions of potentially habitable worlds. The paradigm shifted because the evidence became overwhelming. Skeptics could no longer point to gaps in the data or uncertainties in the models. The patterns were clear, and they told a consistent story. This turning point had profound implications. For the first time in history, scientists could say with confidence that Earth is not unique in its size, composition, and location. The idea that we might be alone in the galaxy, once a reasonable position, now seemed statistically unlikely. If billions of planets resemble Earth in basic properties, then the question of life elsewhere shifts from if to where and when. This shift energized the field of astrobiology, the study of life in the universe. Researchers who had been working on hypothetical scenarios now had real targets to study. The search for biosignatures, once a distant dream, became a concrete goal. Missions were proposed, instruments were designed, and funding was allocated, all driven by the realization that the galaxy is filled with places where life might exist. The paradigm shift also influenced public perception. In earlier decades, the idea of extraterrestrial life was often associated with science fiction, with little green men and flying saucers. The discovery of thousands of exoplanets, many of them potentially habitable, grounded the conversation in science. Life beyond Earth was no longer a fringe idea but a legitimate scientific question. Polls showed that a majority of people believed life exists elsewhere in the universe, and many thought it would be discovered within their lifetimes. This shift in public attitude reflected the broader cultural impact of the discoveries. Humanity was beginning to see itself not as isolated, but as part of a larger cosmic community. The turning point also highlighted the power of statistics and probability. In the absence of direct evidence for life, the statistical argument became central. If there are billions of Earth-like planets, and if life arises even occasionally when conditions are right, then the galaxy should host many instances of life. This reasoning, rooted in the Copernican principle, assumes that Earth is not special, that the processes that led to life here are not unique. The paradigm shift was therefore not just about planets, but about perspective. It was a move away from exceptionalism toward a more humble, more inclusive view of our place in the cosmos. Yet the shift also brought new challenges. With abundance came the problem of selection. If there are billions of potentially habitable planets, which ones should we study first? How do we prioritize? Distance is one factor. Closer planets are easier to observe and characterize. Stellar type is another. Planets around sun-like stars may be more familiar, while those around red dwarfs raise questions about flares and tidal locking. The presence of certain gases, detected through preliminary spectroscopy, might also guide the search. The paradigm shift from scarcity to abundance required a new framework for decision-making, a way to focus limited resources on the most promising targets. The turning point also influenced how scientists thought about the Drake equation, the famous formula for estimating the number of communicative civilizations in the galaxy. One of the terms in that equation is the fraction of stars with planets, and another is the number of planets per star that could support life. Before Kepler, these terms were highly uncertain, little more than guesses. After Kepler, they were grounded in data. The fraction of stars with planets appeared to be close to 1, and the number of potentially habitable planets per star was often 1 or more. This shifted the uncertainty in the Drake equation to other terms. The fraction of habitable planets where life actually arises, the fraction where life becomes intelligent, and the longevity of civilizations. These remain unknown, but the paradigm shift at least narrowed the unknowns, moving the conversation forward. The turning point was also emotional. For many scientists, the realization that Earth-like planets are common was both humbling and exhilarating. Humbling because it confirmed that we are not the center of the universe, not unique, not privileged. Exhilarating because it opened the possibility of connection, of finding cousins among the stars, of discovering that we are part of a larger story. The paradigm shift was not just intellectual but existential. It changed how people thought about themselves, their planet, and their future. In the broader arc of human knowledge, this turning point will be remembered as one of the great revelations. It ranks alongside the discoveries that Earth orbits the Sun, that stars are distant suns, that galaxies are islands of stars scattered across space. Each of these discoveries expanded our sense of scale and diminished our stunned sense of centrality. The realization that Earth-like planets are common is the latest in this series, a step toward understanding the universe not as a backdrop to human existence, but as a vast, populated realm of which we are a small part. The paradigm had shifted, and there was no going back. The galaxy, once mysterious and unknowable, had revealed itself as fertile, abundant, and full of possibility. The realization that billions of Earth-like planets exist in the galaxy did not remain confined to academic journals and scientific conferences. It rippled outward, touching fields far removed from astronomy, influencing culture, philosophy, education, and even politics. The immediate consequence was a reshaping of how humanity thought about itself and its future. If Earth is one among billions, then the questions we ask about our planet, about life, about our responsibilities, take on new dimensions. The discovery was not just a fact to be catalogued, but a catalyst for reflection, a prompt to reconsider assumptions that had gone unexamined for centuries. The ripple effect was subtle at first, felt most strongly by those working directly in science, but it gradually spread, reaching classrooms, boardrooms, religious institutions, and living rooms around the world. One of the most immediate consequences was the surge of interest in astrobiology. This interdisciplinary field, which studies the origin, evolution, distribution, and future of life in the universe, had existed for decades, but it had often struggled for funding and recognition. The discovery of thousands of exoplanets and the evidence that many were potentially habitable changed that. Space agencies prioritized missions aimed at detecting biosignatures. Conferences on astrobiology grew larger, attracting scientists from diverse backgrounds, biologists, chemists, geologists, astronomers, all working together to understand the conditions that allow life to arise and persist. The ripple effect here was institutional, reshaping priorities and creating opportunities for a new generation of researchers. In education, the discoveries transformed how science was taught. Teachers no longer spoke of the solar system as the only known planetary system. Students learned about Kepler, TESS, and the James Webb Space Telescope. They studied exoplanets by name: Kepler 452b, Proxima Centauri b, TRAPPIST 1e. The sense that space exploration was something happening now, not just in history or the distant future, energized classrooms. Young people grew up knowing that the galaxy is filled with worlds, and that some of those worlds might harbor life. This shift in perspective, subtle but profound, influenced career choices. More students pursued degrees in astronomy, planetary science, and related fields, inspired by the possibility of discovering or studying another Earth. The ripple effect was generational, planting seeds that would grow into the next wave of discoveries. Culturally, the consequence was a shift in how humanity saw itself. For much of history, Earth was thought to be the center of creation, the only world that mattered. Even after Copernicus, even after the realization that we orbit an ordinary star in an ordinary galaxy, there remained a sense that Earth was unique as a home for life. The discovery that billions of similar worlds exist challenged this last vestige of centrality. It suggested that life, if it exists elsewhere, is not a miracle confined to one planet, but a natural outcome repeated across the cosmos. This realization was humbling, but it was also connecting. It implied that we are not alone in principle, even if we are alone in practice, separated by vast distances from any potential neighbors. The cultural ripple was therefore paradoxical, reducing our sense of uniqueness while expanding our sense of kinship with the universe. Religious communities responded in varied ways, and the ripple effect here was complex. Some traditions embraced the discoveries as evidence of divine creativity, arguing that a God capable of creating billions of worlds is even more awe-inspiring than one who created only Earth. Others wrestled with theological questions. If life exists elsewhere, does it have a soul? Was there an equivalent to the events described in sacred texts? How does the discovery fit into doctrines of salvation, purpose, or creation? These were not easy questions, and they prompted serious debate within and between faith communities. For some, the discoveries deepened faith. For others, they prompted a re-examination of beliefs. The ripple effect was spiritual, touching on the deepest questions of meaning and existence. In politics and policy, the consequence was more subtle but still significant. Space agencies, recognizing the public interest in exoplanets and the search for life, adjusted their priorities. Missions like the James Webb Space Telescope, the Nancy Grace Roman Space Telescope, and future concepts like the Habitable Exoplanet Observatory received support in part because they spoke to this broader interest. Governments saw space exploration not just as a scientific endeavour, but as a source of inspiration and national pride. International collaborations strengthened, with agencies from different countries pooling resources to build telescopes and analyse data. The ripple effect here was cooperative, fostering partnerships that transcended borders. The discovery also influenced how people thought about Earth itself. If there are billions of other worlds, some potentially habitable, why not move to one of them if Earth becomes uninhabitable? This idea, appealing in science fiction, faced the harsh reality of distance. The nearest potentially habitable planet, Proxima Centauri b, is over 4 light-years away. With current technology, reaching it would take tens of thousands of years. The ripple effect here was a renewed appreciation for Earth. The discovery of other worlds did not diminish our planet's importance. It highlighted its value. Earth is not just one among billions in an abstract sense. It is the one we can reach, the one we can touch, the one we depend on. The consequence was therefore a paradox. The more we learned about other planets, the more we valued our own. In media and popular culture, the ripple was immediate and visible. News outlets covered each major discovery, often with dramatic headlines and artist renderings of alien landscapes. Documentaries explored the implications, asking what it would mean to find life elsewhere. Science fiction, already rich with stories of other worlds, found new inspiration in real data. Writers set stories on Kepler planets, Trappist worlds, imagining societies, ecosystems, and conflicts grounded in actual science. The ripple effect was creative, enriching culture with narratives that blended fact and imagination. The immediate consequence of discovering billions of Earth-like planets was therefore not a single event, but a cascade of responses across multiple domains. It reshaped science, education, culture, religion, policy, and art. It touched individuals, institutions, and societies. The ripple spread outward, carried by the simple, profound realization that Earth is not alone. The galaxy is filled with worlds, and that changes everything. The immediate ripple of discovery, powerful as it was, represented only the beginning of a much longer process. The true impact of realizing that billions of Earth-like planets exist in the galaxy would unfold over generations, shaping not just scientific research, but the trajectory of human civilization. History shows that paradigm shifts in understanding often take decades or even centuries to fully manifest. The heliocentric model, the theory of evolution, the recognition of deep time. Each of these revelations reshaped how people saw the world, but their full impact emerged, slowly, through education, cultural absorption, and the gradual replacement of old assumptions with new ones. The discovery of exoplanetary abundance was no different. Its echoes would reverberate through time, influencing future generations in ways that those living through the initial discoveries could only begin to imagine. One of the most profound long-term impacts was on the philosophy of human existence. For millennia, questions about our place in the universe were answered through myth, religion, and speculation. Are we alone? Are we special? Is Earth the only home for life? These questions shaped cultures, influenced ethics, and provided frameworks for meaning. The discovery that Earth-like planets number in the billions did not answer all these questions, but it shifted the ground on which they were asked. It made the possibility of life elsewhere not just plausible, but statistically likely. Over time, this shift influenced how people thought about purpose, identity, responsibility. If life is common, then humanity is not the endpoint of cosmic evolution, but one chapter in a much larger story. This realization, absorbed gradually through generations, fostered a sense of humility and connection, a recognition that we are part of a broader tapestry of existence. The impact on science was equally profound and enduring. The discovery of exoplanetary abundance redirected research priorities for decades. Funding flowed into new missions, new telescopes, new instruments designed to study distant worlds in ever greater detail. By the mid-21st century, scientists were not just detecting planets, but characterizing them, measuring their atmospheric compositions, detecting biosignatures, and perhaps even imaging their surfaces. This progression, made possible by the initial Kepler discoveries, represented a transformation in astronomy. The field moved from being purely observational, cataloguing distant objects, to being investigative, asking questions about the nature and habitability of those objects. The echoes of the paradigm shift reverberated through every branch of planetary science, influencing how researchers studied not just exoplanets, but planets in our own solar system, applying lessons learned from afar to understanding home. Culturally, the impact deepened over time. The first generation to grow up knowing that the galaxy is filled with planets thought differently about space, exploration, and humanity's future. They did not see space as empty, but as populated with possibilities. This shift influenced literature, film, art, and music, all of which began to reflect a more nuanced, scientifically grounded vision of the cosmos. Stories set on real exoplanets became common, blending hard science with imaginative speculation. Artists created works inspired by the idea of distant Earths, landscapes we might never see but know must exist. Musicians composed pieces evoking the vastness and solitude of space, but also the connection implied by shared existence. The cultural echo was not loud, but it was persistent, shaping the creative output of an era. The impact on technology was also significant. The drive to study exoplanets pushed the development of new instruments, advanced spectrographs, space-based telescopes, coronagraphs, star shades, adaptive optics. These technologies, developed for astronomy, often found applications elsewhere. Techniques for detecting faint signals in noisy data, refined for finding planets, were applied to medical imaging, communications, and data science. The materials and engineering solutions developed for space missions influenced industries on Earth. The echo here was practical, a reminder that fundamental research often yields unexpected benefits. Over the longer term, the discovery influenced humanity's approach to existential questions. If billions of Earth-like planets exist, and if even a small fraction are inhabited, then the question of contact becomes real. Should we send messages into space? Should we listen for signals from others? What would we say if we made contact? These questions, once abstract, took on urgency. Organizations dedicated to the search for extraterrestrial intelligence, SETI, received renewed attention and support. Philosophers and ethicists began to debate the implications of contact. What responsibilities do we have to other civilizations? How should we represent ourselves? The echoes of the discovery extended into these debates, shaping how humanity prepared for a future that might include interaction with other intelligent beings. The impact also touched on environmentalism and planetary stewardship. Knowing that other Earth-like planets exist did not provide an escape hatch from the challenges facing our own planet. The distances were too great, the technology too limited. Instead, the knowledge reinforced the preciousness of Earth. If habitable planets are common in the galaxy, but none are within reach, then the one we have becomes all the more valuable. This realization, echoing through time, influenced environmental movements, space policy, and public discourse about sustainability. The discovery of other Earths paradoxically strengthened the case for protecting this one. In education, the long-term impact was transformative. Curricula evolved to include exoplanet science as a core topic, not an optional add-on. Students learned about the methods of detection, the statistics of abundance, the search for biosignatures. They studied the diversity of planetary systems and the factors that make a planet habitable. This education shaped how future generations thought about the universe and their place in it. It fostered scientific literacy, critical thinking, and a sense of wonder that persisted into adulthood. The echo here was cognitive, altering the baseline knowledge and perspective of an entire generation. The echoes through time also included the gradual normalization of the idea that we are not alone. What had once been a radical, even frightening concept became familiar, almost mundane. By the late 21st century, the possibility of life on other planets was widely accepted, discussed in schools, portrayed in media, and integrated into cultural narratives. The shock of the initial discovery faded, replaced by a quiet expectation. This normalization was itself a profound impact, a sign that humanity had absorbed the paradigm shift and moved on, no longer questioning whether other worlds exist, but asking what those worlds are like and whether we will ever know. Behind every discovery, every data set, every statistical model, there are people. The story of finding billions of Earth-like planets in the galaxy is not just a story of telescopes and algorithms, but of the dreamers, the scientists, engineers, and visionaries who dedicated their lives to answering a question that had haunted humanity for millennia. These individuals came from diverse backgrounds, different countries, different disciplines, united by a shared curiosity. They worked long hours analyzing data, writing code, building instruments, often with little recognition and uncertain funding. They faced setbacks, technical failures, and skepticism, yet they persisted, driven by the belief that the universe had secrets worth uncovering. The human element of this story is as important as the scientific achievements, because it reminds us that exploration is not just about what we find, but about the passion and persistence required to search. One of the central figures in this story is William Borucki, the principal investigator of the Kepler mission. For decades, Borucki championed the idea of using the transit method to find planets. He faced repeated rejections from NASA, his proposals turned down multiple times because the technology was considered too risky, too difficult, too uncertain. He refined his ideas, gathered a team, and eventually convinced NASA that the mission could succeed. When Kepler launched in 2009, it was the culmination of more than 20 years of effort. Borucki's persistence exemplifies the human element, the refusal to accept that a question is unanswerable simply because it is hard. Another key figure is Michel Mayor, one of the Swiss astronomers who discovered the first exoplanet around a sun-like star in 1995. Mayor and his colleague Didier Queloz were not looking for fame. They were pursuing a scientific question, using a technique they had painstakingly developed to measure the radial velocities of stars. Their discovery of 51 Pegasi b was a surprise, even to them, but it opened the floodgates. Mayer continued to contribute to the field for decades, discovering more planets, refining methods, and inspiring a new generation of researchers. In 2019, he and Queloz were awarded the Nobel Prize in Physics, recognition of their groundbreaking work. Yet for Mayer, the reward was never the prize, but the process, the joy of discovery itself. Behind the famous names are thousands of others whose contributions were equally essential. The engineers who designed Kepler's photometer, the instrument that measured starlight with unprecedented precision, the software developers who wrote the algorithms to sift through millions of light curves, identifying the faint signatures of transits, the graduate students who spent years analyzing data, confirming planets one by one, often receiving little credit for their painstaking work, the technicians who maintained telescopes, the administrators who secured funding, the educators who communicated the findings to the public. Each of these individuals played a role, and together they formed a community dedicated to a common goal. The human element also includes the failures and disappointments. Not every mission succeeded. Not every proposal was funded. Not every candidate planet turned out to be real. Kepler itself suffered a critical failure in 2013 when reaction wheels that stabilized the spacecraft malfunctioned. For a time, it seemed the mission was over. Yet the team adapted, finding a new way to use the spacecraft by balancing it against the pressure of sunlight. This improvisation, known as the K2 mission, allowed Kepler to continue discovering planets for several more years. The resilience shown by the team, their refusal to give up when faced with technical challenges, is part of the human story. Science is not a smooth path. It is filled with obstacles, and progress requires not just intelligence, but determination. The dreamers also include those who inspired the search through their writings and advocacy. Carl Sagan, though he passed away in 1996, laid much of the intellectual groundwork for the search for extraterrestrial life. His work on the Voyager Golden Record, his advocacy for planetary exploration, and his ability to communicate the wonder of the cosmos to the public all contributed to the cultural context in which missions like Kepler were conceived. Sagan's vision of a universe filled with life influenced a generation of scientists, many of whom cite him as the reason they entered the field. His human element was inspiration, the ability to make people care about questions that seemed abstract or distant. The diversity of the people involved also mattered. The search for Earth-like planets was a global effort, involving scientists from the United States, Europe, Asia, Latin America, and beyond. Women and men from different cultures and backgrounds brought different perspectives, different skills, and different ways of thinking about problems. This diversity enriched the research, leading to more robust methods and more creative solutions. The human element here is collaboration, the recognition that the biggest questions require collective effort, that no single person or the nation can answer them alone. The emotional dimension of the search is also part of the human story. For many scientists, the discovery of an Earth-like planet was not just a professional achievement, but a deeply personal moment. It was the realization of a dream, the confirmation that the universe is more wondrous than they had hoped. Some described tears of joy when Kepler's first Earth-sized planets in habitable zones were confirmed. Others spoke of a sense of connection, a feeling that they were part of something larger than themselves. These emotional responses are not separate from the science. They are part of what drives it, what sustains it through the difficult years. The dreamers also include those who came before, the astronomers and philosophers who speculated about other worlds long before any evidence existed. Giordano Bruno, who in the 16th century argued that stars are suns with their own planets, and who was burned at stake in part for these beliefs. Christian Huygens, who in the 17th century wrote about the possibility of life on other worlds. Percival Lowell, who in the early 20th century believed he saw canals on Mars, evidence of a civilization. Though Lowell was wrong, his passion for the question inspired others. The human element stretches back through history, a chain of curiosity connecting past to present. The path to establishing that billions of Earth-like planets exist in the galaxy was not smooth or unopposed. Science thrives on skepticism, on the rigorous testing of ideas, on the demand for evidence before claims are accepted. The discovery of exoplanets and the statistical arguments for their abundance face scrutiny from multiple directions. Some questioned the methods, others the interpretations, and still others the broader implications. This opposition was not malicious, but essential. It forced proponents to refine their arguments, strengthen their evidence, and acknowledge uncertainties. The battle for truth was not a conflict between good and evil, but a dialectical process through which science advances, testing claims against counterclaims, evidence against doubt, until a consensus emerges. This process, though sometimes contentious, is what gives scientific conclusions their strength. One of the earliest forms of opposition came from those who doubted the transit method itself. When Kepler was proposed, some astronomers argued that the dimming caused by an Earth-sized planet would be too small to detect reliably. They pointed to the noise in stellar brightness, the variability of stars, the limitations of instruments. They questioned whether the spacecraft could maintain the stability needed to measure such faint signals over years. These were legitimate concerns, and they required careful responses. The Kepler team conducted extensive testing, built prototypes, and demonstrated that the technology could work. The opposition, in this case, made the mission stronger by forcing the team to prove that their methods were sound. After Kepler began returning data, a new form of opposition emerged: skepticism about the interpretation of the results. Some scientists questioned whether the signals attributed to planets were really caused by planets. Could they be artifacts of the data processing? Could they be eclipsing binary stars masquerading as planets? Could they be noise that happened to repeat periodically? These questions were addressed through follow-up observations, independent confirmation, and statistical analysis. The Kepler team developed rigorous criteria for validating planets, requiring multiple transits, consistency in depth and duration, and ruling out alternative explanations. The opposition here was methodological, a demand for higher standards of proof, and the field rose to meet it. The statistical arguments for planetary abundance also faced opposition. Some argued that the corrections for observational biases were too aggressive, that the models overestimated the number of undetected planets. Others questioned the definition of habitable zone, pointing out that being in the zone does not guarantee habitability. They noted that Venus and Mars both lie within or near the Sun's habitable zone, yet neither is habitable. The opposition argued that the headline numbers, billions of Earth-like planets, were misleading, that they implied more certainty than the data warranted. This critique was fair, and it led to more careful language in scientific papers and presentations. Researchers began to distinguish between planets in the habitable zone and truly habitable planets, acknowledging that the former is a necessary but not sufficient condition for the latter. The rare Earth hypothesis, articulated by Peter Ward and Donald Brownlee, represented a more philosophical opposition. It did not dispute the existence of billions of planets, but it questioned whether most of them could sustain life. The hypothesis argued that Earth's habitability is the result of many factors working together: plate tectonics, a large moon, a magnetic field, a stable star, Jupiter's gravitational shield. It suggested that while planets in habitable zones may be common, planets with all the necessary conditions for complex life are rare. This opposition was not about data, but about interpretation. It asked whether the optimism of the mediocrity principle was justified, or whether Earth is more exceptional than we want to believe. The debate between these perspectives continues, and it has been productive, prompting research into the factors that contribute to long-term habitability. Another form of opposition came from those concerned about overhyping the findings. Some scientists worried that the media's focus on Earth twins and the possibility of life created unrealistic expectations. They argued that even if billions of Earth-like planets exist, we may never be able to study them in detail, and we may never detect life. They cautioned against promising too much, fearing that disappointment could lead to a loss of public support and funding. This opposition was pragmatic, a concern for the long-term health of the field. It led to efforts to communicate findings more carefully, emphasizing what is known and what remains uncertain. There was also opposition from outside the scientific community. Some religious groups initially resisted the idea that Earth is not unique, seeing it as a challenge to doctrines of human specialness. Others embraced the findings but questioned their theological implications. These debates, while not scientific, were part of the broader cultural response. They showed that the discovery of exoplanets touched on deeply held beliefs, and that opposition sometimes came from a desire to preserve meaning and identity in the face of change. Over time, many religious communities found ways to integrate the findings into their worldviews, seeing them as evidence of divine creativity rather than a threat. The battle for truth also involved self-correction within the scientific community. Early estimates of planetary abundance varied widely, from a few billion to tens of billions, depending on the assumptions. As more data became available, the estimates converged, but the process was messy. Some papers overestimated, others underestimated, and debates in the literature could be sharp. This process, though sometimes uncomfortable, is how science works. Ideas are proposed, tested, critiqued, and refined. The opposition, in this sense, is not an obstacle but a mechanism, a way to ensure that conclusions are robust and well supported. One of the most important aspects of the opposition was that it demanded transparency. Critics insisted on access to data, on clear descriptions of methods, on reproducibility of results. The Kepler team, and others in the field, responded by making data publicly available, publishing detailed papers, and inviting independent analysis. Openness strengthened the findings. When independent teams, using different methods, arrived at similar conclusions, the case for planetary abundance became much stronger. The opposition, by demanding rigor and transparency, helped build the consensus that now exists. The battle for truth was therefore not a hindrance, but a necessity. It ensured that the claim, billions of Earth-like planets exist in the galaxy, was supported by solid evidence, rigorous methods, and careful reasoning. It reminded scientists to be humble, to acknowledge uncertainties, and to avoid overreaching. And it demonstrated that science, at its best, is a self-correcting process where opposition and critique lead not to stagnation but to progress. As the evidence accumulated, as the debates matured, and as the initial shock of discovery gave way to deeper reflection, something shifted within the scientific community and beyond. It was not a sudden revelation, but a gradual awakening, a new awareness that the galaxy is not what previous generations imagined. This awareness was not just intellectual, but existential. It touched on how people understood their place in the cosmos, how they thought about the future, and how they valued the present. The awakening was the realization that we live in a universe far richer and more complex than the simple models of the past suggested. Earth is not alone. The conditions that allow life to flourish are not unique. The galaxy is filled with worlds, and among them are likely many that resemble home. This awareness changed everything, not by altering the facts of daily life, but by reshaping the context in which those facts are understood. For scientists, the awakening came through the data. As the catalogue of exoplanets grew, patterns emerged that could not be ignored. Planets were not rare exceptions but common outcomes. Small, rocky worlds in habitable zones appeared again and again. The galaxy, once a vast emptiness punctuated by occasional stars, now appeared as a crowded neighborhood filled with systems, orbits, and possibilities. This shift in perception was profound. Astronomers who had spent their careers studying stars began to think of those stars as suns, each potentially hosting families of worlds. The awakening here was a move from abstraction to concreteness, from possibility to probability. For the public, the awakening was more gradual, but equally significant. It came through education, through media coverage, through conversations with friends and family. People began to internalize the idea that the stars they saw at night were not just distant lights, but places. They began to imagine what those places might be like, to wonder whether anyone or anything was looking back. This shift in imagination was subtle but powerful. It transformed the night sky from a passive backdrop into an active presence, a reminder that the universe is alive with potential. The awakening here was emotional, a sense of connection to something larger. The new awareness also brought a sense of humility. To realize that Earth is one among billions is to confront the limits of human centrality. We are not the focus of creation. We are not the endpoint of cosmic evolution. We are one outcome among many, shaped by the same processes that have shaped countless other worlds. This humility was not diminishing, but liberating. It freed people from the burden of exceptionalism, from the need to see themselves as uniquely important. It allowed a broader perspective, one in which humanity is part of a larger story, connected to the cosmos not by uniqueness, but by commonality. The awakening also influenced how people thought about life. If the conditions for life are common, then life itself may be common. This possibility, once speculative, now felt within reach of confirmation. The search for biosignatures, the analysis of exoplanet atmospheres, the possibility of detecting signs of life within a generation, all became real goals. The awareness that we might soon know whether we are alone changed the tenor of the conversation. It was no longer a distant dream, but an imminent question. The awakening here was anticipation, a sense that we are living at a threshold on the verge of one of the greatest discoveries in human history. The new awareness extended to our understanding of habitability itself. Early in the search, Habitability was often equated with being in the right zone, at the right distance from a star. But as knowledge deepened, it became clear that habitability is far more complex. It involves atmospheres, geology, magnetic fields, stellar activity, and time. A planet can be in the habitable zone and still be barren. Conversely, moons far from the traditional zone, like Europa, can harbour subsurface oceans. The awakening here was a recognition of complexity, an understanding that nature does not follow simple rules but creates diversity through the interplay of many factors. This awareness made the search more nuanced, more sophisticated, and more exciting. The awakening also touched on the concept of time. The discovery of Earth-like planets was not just about the present, but about the past and future. Some of these planets may have hosted life for billions of years, civilizations that rose and fell long before Earth even formed. And others may be in their twilight, their stars swelling into red giants, their oceans boiling away. The awareness of this temporal dimension added depth to the story. It reminded people that the universe is not static, but dynamic, constantly changing, constantly creating and destroying. For some, the awakening brought a sense of responsibility. If Earth is one among many habitable planets, then our treatment of it takes on new significance. We cannot claim that Earth is irreplaceable if billions of alternatives exist, yet the distances make those alternatives irrelevant. Earth is the only planet we can touch, the only one we can protect or harm. The awareness that other Earths exist did not provide an escape, but a mirror reflecting back the preciousness of this one. The awakening here was ethical, a recognition that stewardship of our planet is not just a practical necessity, but a moral duty. The new awareness also influenced art and culture. Writers, filmmakers, and artists began to explore themes of cosmic plurality, the idea that we are part of a larger community of worlds. Stories set on exoplanets became more common, grounded in real data, exploring what life might be like on worlds with different stars, different atmospheres, different histories. Music and visual art reflected the sense of wonder and connection, using imagery and sound to evoke the vastness and intimacy of the cosmos. The awakening here was creative, inspiring new ways of expressing the human relationship with the universe. In the end, the awakening was a shift from isolation to connection. For centuries, humanity had looked at the stars and felt alone, separated by vast distances from anything familiar. The discovery of billions of Earth-like planets did not eliminate the distance, but it changed the meaning of the emptiness. We are no longer alone in principle. We share the galaxy with countless worlds, some barren, some perhaps alive. This awareness, once fully absorbed, transforms how we see ourselves. We are no longer solitary travelers, but part of a larger journey, participants in a cosmic story that is still being written. After all the data, all the debates, all the refinements and recalculations, a simple truth emerged, one that could be stated clearly and with confidence. The Milky Way galaxy, our home among the cosmos, likely contains tens of billions of Earth-like planets. This was not speculation. It was not hope dressed as science. It was a conclusion grounded in observation, supported by statistics, confirmed by independent studies. The revelation was both staggering and humbling. Staggering because the number is so vast it challenges comprehension. Humbling because it places Earth in context, one world among countless others. This deepest truth, the core finding of decades of research, reshaped humanity's understanding of the universe and its place within it. It answered an ancient question: Are there other worlds like ours? With a resounding yes, and in doing so, it opened 1,000 new questions. The revelation rested on several pillars of evidence. The first was the sheer abundance of planets. Nearly every star observed by Kepler and other missions appeared to host at least one planet. The idea that planetary systems are rare, that our solar system is an exception, had been decisively refuted. Planets are the rule, not the exception. They form naturally when stars form, condensing from the same disk of gas and dust that gives birth to the star itself. This process is common throughout the galaxy, which means planets are common as well. The first pillar of the revelation was ubiquity. Planets are everywhere. The second pillar was the frequency of small, rocky planets. Early exoplanet discoveries were dominated by gas giants, large planets that produce strong signals. But as detection methods improved, smaller planets came into view. Kepler's data showed that rocky planets, similar in size to Earth, are not rare. They appear around many types of stars, from sun-like yellow dwarfs to cooler red dwarfs. The discovery of thousands of such planets provided the statistical basis for estimating their total number in the galaxy. The second pillar was prevalence. Small rocky planets are common. The third pillar was the habitable zone. For a planet to be Earth-like, it must orbit at a distance where temperatures allow liquid water to exist. Kepler's mission specifically targeted stars to search for planets in this zone. The results were striking. Roughly 10 to 20% of Sun-like stars appeared to host an Earth-sized planet in the habitable zone. This fraction, applied to the tens of billions of Sun-like stars in the galaxy, yielded billions of candidates. For red dwarfs, which are even more common, the fraction might be higher, potentially 30 to 50%. The third pillar was placement. Many planets orbit in the right zone. The fourth pillar was the consistency of the findings. Multiple independent studies, using different methods and different data sets, arrived at similar conclusions. This convergence of evidence was crucial. When a single study makes a bold claim, skepticism is warranted. But when many studies, conducted by different teams, using different approaches, all point in the same direction, the claim gains credibility. The fourth pillar was reproducibility. The results held up under scrutiny. Together, these pillars supported the revelation. The Milky Way contains hundreds of billions of stars. Most of those stars have planets. A significant fraction of those planets are small and rocky. Many of those rocky planets orbit in habitable zones. Even conservative estimates place the number of potentially Earth-like planets in the tens of billions. This is the deepest truth, a fact as well established as the existence of galaxies or the expansion of the universe. Yet the revelation also came with caveats. Being Earth-like in size and orbit does not guarantee habitability. A planet may lack an atmosphere, or have the wrong chemistry, or be geologically dead. It may orbit a star that flares violently, sterilizing its surface. It may be tidally locked, with one side in perpetual daylight and the other in darkness. The revelation tells us that the ingredients are common, but it does not guarantee that the recipe works everywhere. This nuance is important. The deepest truth is not that billions of planets are habitable, but that billions of planets have the potential for habitability. The distinction is subtle but significant. The revelation also raised profound philosophical questions. If tens of billions of Earth-like planets exist, how many are inhabited? If even a small fraction harbour life, the galaxy could be teeming with biology. If life is common, how often does it become complex? How often does it develop intelligence? The revelation about planets shifts the focus to these harder, deeper questions. It moves the conversation from whether other Earths exist to what those Earths are like and whether we will ever know. For many, the revelation was a moment of awe. To contemplate tens of billions of worlds, each potentially unique, each with its own story, is to glimpse the immensity of the cosmos. It is to realize that the universe is far more generous with possibilities than we ever imagined. The deepest truth is not just about numbers, but about potential. Each of those billions of planets is a world, a place where clouds might gather, where mountains might rise, where oceans might lap against shores. We may never visit them, but they are real, and their existence changes how we see the stars. The revelation also brought a sense of connection. We are not alone in the galaxy, not in the sense of confirmed contact, but in the sense of kinship. The processes that shaped Earth have shaped countless other worlds. The chemistry of life, if it exists elsewhere, is likely similar to our own, based on carbon, water, and energy. The revelation is that we are part of a larger pattern, a cosmic thread woven through the galaxy. This connection is abstract, separated by distances too vast to cross, but it is real. The deepest truth, ultimately, is this. The galaxy is not a barren place with a few scattered oases. It is fertile, abundant, filled with the potential for worlds like ours. The numbers may vary depending on definitions and assumptions, but the core finding remains. Earth-like planets are common. They number in the tens of billions. They are out there, circling distant stars, waiting to be understood. This revelation is one of the great achievements of modern science, a testament to human curiosity, ingenuity, and persistence. What does it mean to live in a galaxy filled with tens of billions of Earth-like planets? The question is not scientific, but philosophical. It asks not about facts, but about implications, about how this knowledge changes our understanding of ourselves, our planet, and our future. The revelation that Earth is one among many invites reflection, a pause to consider what has been learned and what it signifies. This reflection is not a single moment, but an ongoing process, one that will continue for generations as humanity absorbs the meaning of the discovery. It is a quiet, contemplative space where wonder meets wisdom, where the enormity of the cosmos is felt not through numbers, but through thought. One of the first reflections is on the nature of uniqueness. For most of human history, Earth was thought to be singular, the only world of its kind. This belief was comforting in some ways, suggesting that humanity mattered, that our existence was not accidental, but it was also isolating, placing us alone in a vast, empty universe. The discovery that billions of similar worlds exist challenges the notion of uniqueness, but it does not eliminate it. Earth may not be unique in size or orbit, but it is unique in detail. No two planets are identical. Each has its own history, its own chemistry, its own story. The reflection here is that uniqueness is not about being the only one, but about being unrepeatable. Earth is unique not because it is alone, but because it is itself irreplaceable in its particularity. Another reflection concerns the concept of home. If other Earths exist, could we move to them? The distances say no. Even the nearest potentially habitable planet, Proxima Centauri b, is over 4 light-years away, unreachable with current technology. The dream of finding a new home among the stars remains distant. This realization reinforces the value of Earth. It is not just one option among many. It is the only home we have, the only place within reach where we can live. The reflection here is that abundance elsewhere does not diminish scarcity here. Earth is irreplaceable not because no other planets exist, but because no other planets are accessible. This makes our responsibility to care for Earth all the more urgent. A third reflection is on the possibility of life. If billions of planets have the right conditions, how many are inhabited? The question has no answer yet, but pondering it is itself meaningful. It forces us to confront our assumptions about life, about whether it is rare or common, fragile or resilient. It invites us to imagine ecosystems we have never seen, organisms adapted to different gravities, different atmospheres, different stars. The reflection here is on the creativity of nature, on the idea that life may be more diverse and widespread than we currently know. Even without proof, the possibility changes how we see the universe, transforming it from a lifeless expanse into a potential garden of biological variety. The reflection also touches on time. The planets we have discovered are not all the same age. Some may be older than Earth. Their stars formed billions of years before the Sun. If life arose on those planets, it has had more time to evolve, perhaps into forms we cannot imagine. Other planets are younger, still cooling, still assembling. Their stories are just beginning. The reflection here is on the vastness of time, on the idea that the universe is not static, but constantly changing. We are living at one moment in a cosmic timeline that stretches far into the past and future. The planets we detect today are snapshots, frozen in time by the speed of light. By the time their light reaches us, they may have already changed. Another layer of reflection is ethical. If other planets exist, and if they harbour life, what responsibilities do we have? Should we protect them from contamination? Should we seek to contact them? Should we leave them undisturbed? These questions, once hypothetical, are becoming practical as our technology advances. The reflection here is on the ethics of exploration, on the need to balance curiosity with caution. Humanity's history of exploration on Earth is filled with examples of harm caused by contact, ecosystems disrupted, cultures destroyed. The reflection is whether we can do better, whether we can explore the cosmos without repeating the mistakes of the past. The reflection also extends to meaning. For many people, the sense of meaning in life comes from connections, to family, to community, to purpose. The discovery that we may be part of a larger cosmic community, one that includes other worlds and possibly other life, expands the sense of connection. It suggests that we are not isolated, not cut off from the rest of existence. The reflection here is on belonging, on the idea that humanity is part of a broader tapestry woven into the fabric of the galaxy. This belonging does not require contact or communication. It is enough to know that we are not alone in principle, that the conditions that gave rise to us have likely given rise to others. The reflection is that meaning can be found not just in what we do, but in what we are part of. There is also a reflection on mystery. Even with all the data, all the telescopes, all the statistical models, much remains unknown. We do not know which of the billions of Earth-like planets are truly habitable. We do not know how many harbour life. We do not know whether any host intelligence. The mystery is not a failure of science, but a feature of the universe. It is a reminder that no matter how much we learn, there will always be more to discover. The reflection here is on the value of questions, on the idea that not knowing is not a weakness, but an invitation. The mystery keeps us curious, keeps us searching, keeps us humble. Another reflection is on perspective. When you look at Earth from space, the famous overview effect, national borders disappear, conflicts seem petty, and the fragility of the planet becomes apparent. The discovery of billions of other Earths creates a similar shift, but on a larger scale. It is a cosmic overview effect, a realization that our planet is one small part of a much larger whole. The reflection here is on scale, on the idea that the problems we face, important as they are, exist within a context so vast that it challenges our sense of proportion. This perspective can be humbling, but it can also be clarifying, helping us see what truly matters. The reflection also includes gratitude. To exist at all is improbable. To exist on a habitable planet with liquid water, breathable air, and stable climates is even more so. To exist at a time when we can detect other planets and understand our place in the galaxy is extraordinary. The reflection here is on the privilege of awareness, on the fact that we are not only alive, but able to contemplate our existence and our context. This gratitude does not come from comparison, from thinking we are better or luckier than others, but from recognition, from seeing the gift of existence clearly. Finally, there is a reflection on hope. The discovery that billions of Earth-like planets exist is, at its core, hopeful. It suggests that the universe is generous with opportunities, that the conditions for life are not impossibly rare, that we may one day find companions among the stars. This hope is not naive. It does not ignore the challenges, the distances, the uncertainties, but it allows for possibility, for the idea that the future may hold discoveries we cannot yet imagine. The reflection here is that hope is not about certainty, but about openness, about being willing to believe that the universe has more to offer than we currently know. Pondering the meaning of billions of Earth-like planets is an exercise in wonder and humility. It is an invitation to think deeply about who we are, where we fit, and what our existence signifies. The meaning is not fixed or final. It will evolve as we learn more, as new discoveries are made, as future generations add their own reflections. But for now, the meaning is this: we are part of something larger, connected to a galaxy filled with worlds, living at a time when we can glimpse that connection and marvel at it. The reflection is not an endpoint, but a beginning, a door opened into deeper questions and richer understanding. As the journey through numbers, data, theories, and reflections draws to a close, it is time to return to where we began, to the night sky, to the quiet wonder of looking up and asking questions. The story of how many Earth-like planets exist in our galaxy has unfolded across decades, shaped by the work of countless individuals, driven by curiosity, persistence. The answer, grounded in observation and analysis, is both astonishing and humbling. Tens of billions of such worlds may circle distant stars, each one a potential cousin of Earth, each one carrying the possibility of oceans, atmospheres, and perhaps even life. This knowledge, hard-won through years of effort, is a legacy that will endure, shaping how future generations see themselves and their place in the cosmos. But with the answer comes a return, a recognition that for all the abundance in the galaxy, we stand on the only world we can truly call home. The legacy of this discovery is multifaceted. Scientifically, it has transformed astronomy, turning the study of exoplanets from a niche pursuit into a central field of research. It has driven the development of new instruments, new missions, new methods of analysis. The James Webb Space Telescope, future observatories, and the techniques of transmission spectroscopy all trace their roots to the question of how many planets exist and what they are like. The legacy here is methodological, a toolkit of approaches that will be used for generations to study the cosmos. Culturally, the legacy is a shift in perspective. Humanity now knows that Earth is one among many, that the galaxy is filled with worlds, and that the conditions for life may be common. This knowledge has seeped into education, media, and public consciousness. Children growing up today learn about exoplanets as a matter of course, not as distant speculation but as established fact. The legacy here is generational, a baseline of understanding that will shape how future societies think about exploration, about the environment, and about the possibility of life elsewhere. Philosophically, the legacy is a deepening of questions. The discovery that billions of Earth-like planets exist does not answer the question of whether we are alone, but it makes the question more urgent and more tractable. It shifts the focus from whether life can exist elsewhere to whether it does, and if so, how often. The legacy here is inquiry, a framework of questions that will guide research for decades or even centuries. The return, the act of coming back to Earth after exploring the question of other worlds, is also significant. For all the wonder of distant planets, for all the statistics and possibilities, Earth remains unique in one critical way. It is here. It is the ground beneath our feet, the air we breathe, the water we drink. The return is a recognition that no matter how many billions of planets exist, this one is ours, and it is irreplaceable. The knowledge of other Earths does not diminish our planet's value. If anything, it enhances it, showing us how rare and precious habitability is, even if it is not unique. The legacy also includes a sense of responsibility, knowing that other habitable planets may exist, but are unreachable, reinforces the need to care for this one. We cannot escape to another Earth if we ruin our own. The distances are too vast, the technology too limited. Earth is not a practice run. It is the only chance we have. The legacy here is stewardship, a recognition that the future of humanity depends on how we treat our planet. The return also brings a sense of peace. The journey through the question of how many Earth-like planets exist has been one of wonder, discovery, and reflection. But it has also shown us that, for now, Earth is enough. It is more than enough. It is a world of beauty, complexity, and life. A place where oceans stretch wide, where mountains rise high, where forests breathe and creatures thrive. The return is a homecoming, a moment to appreciate what we have, while acknowledging that we are part of something larger. The story of Earth-like planets is also a story of human aspiration. It is about the drive to know, to explore, to push beyond the boundaries of what is visible and put it certain. It is about the willingness to ask difficult questions and the patience to wait years or decades for answers. The legacy here is inspiration, a reminder that humanity is capable of extraordinary things when driven by curiosity and united by common purpose. As this chapter closes, imagine once more the night sky. The stars you see are not just distant lights, but suns, each potentially hosting worlds. Among those worlds, tens of billions may be similar to Earth, circling at the right distance, carrying the right conditions. You cannot see them, but they are there, hidden in the vastness, waiting. This knowledge does not make the sky less mysterious, but more so. It fills the darkness with possibility, transforming the emptiness into abundance. The legacy of discovering that Earth-like planets are common is not just scientific, but human. It changes how we see ourselves, not as isolated, but as part of a larger pattern. It invites us to think beyond our immediate concerns, to consider the long arc of cosmic history, and to imagine futures we cannot yet predict. The return, the act of coming back to Earth after this journey, is not a retreat, but a grounding. It is a reminder that exploration begins and ends here, on this small, blue world the only one we can touch. The question of how many Earth-like planets exist in our galaxy has been answered, as well as current knowledge allows. The number is vast, the implications profound. But the deeper truth is not just about the number. It is about what the number reveals, the fertility of the galaxy, the commonality of the conditions that allow life, and the preciousness of the world we inhabit. The legacy is knowledge, perspective, and responsibility. The return is gratitude, wonder, and peace. Together, they form a complete story, one that honors the question, the search, and the home we have always known. As you rest now, let the thought of countless worlds settle gently around you. Let it remind you that the universe is vast, that possibilities abound, but that here, on Earth, you are held safely. The stars continue their silent turning. The planets orbit unseen, and the galaxy unfolds its story across time and space. You are part of that story, connected to it by the very atoms in your body, by the questions you ask, and by the simple act of looking up and wondering. Sleep well, knowing that the cosmos is richer than we ever imagined, and that Earth, our home, is a precious gift among billions of possibilities.